So there are numerous excited atoms which will by itself will come down and emit spontaneously the photons that will be emitted in all possible directions, as I have shown here. Some of these photons which are emitted along the axis will, as it travels, it interact with more excited atoms and will stimulate it to emit more and more similar photons, so the number will multiply. Needless to say, the cavity upon such an integration with such an active medium, where that means where population has been inverted between two energy levels, sets up the working of a laser that we know today. Here you see this is actually schematic representation of the multiplication of photons due to stimulated emission, initiated by the spontaneous emission from a single excited atom inside a simple cavity. It is only one atom, one photon emitted spontaneously in the right direction begins the process. The black dots here represent continuation of the same process. That is, from one photon you have 2, 2 to 4, 4 to 8, 8 to 16, and so on. This way it would multiply. Therefore, a laser can be pictured in the following manner. An active medium, that is a medium in which population has been inverted between two energy levels. And inversion of population means you have created gain between these two energy levels, and you actually place this active media inside the cavity that we discussed till now. Now it is well known that an atom or a molecule can only spend a finite amount of time in an excited state. Because the excited state has higher energy, therefore an atom or molecule, when excited to this state, cannot reside there indefinitely. Because it is a higher energy state, staying there indefinitely will violate the rule of nature. That means an excited state has a finite lifetime. Therefore, in accordance with Heisenberg's uncertainty principle, which says that if you have an energy level, and if the lifetime of the level, say, is delta T, and the energy spread, suppose the spread of energy is delta E, then delta E into delta E must be greater than that Planck's constant. So that means if your delta T is small, that is the finite lifetime, if delta T were infinity, then delta E would have been, it would be narrow, just a single line. But because delta T is finite, so delta E, there will be a corresponding spread in energy. And that is what is shown here. Both these energy levels, because they have a finite lifetime, when an atom is excited to this level, this is the lower energy state here, the ground level may be even lower. So both these energy states have been shown here to be broadened in energy as the result of Heisenberg's uncertainty principle. Hence, the gain that you have created between these two energy levels does not occur on a single frequency. Instead, the gain is distributed on numerous frequencies, as you see here. Of course, the gain is maximum at the central frequency, which is called the line center. Line center is basically the frequency corresponding to this energy value, which is, if it is E0, that is the energy difference between the excited state and the lower energy state. If it is E0, then E0 is equal to H nu 0. So nu 0 we call line center frequency. So nu 0 equal to E0 by H. So this is this frequency. At this frequency where we have actually created gain, the gain max peak, value of the gain peaks here. This is the gain. And it drops off on either side. Hence, the gain that has been created does not occur on a single frequency. Instead, the spread over numerous frequencies are been here. Now you see, all these frequencies has gain. Does it mean that the lasing here will occur on all these frequencies? The answer is an emphatic no. Lasing will occur only on those frequencies which are cavity modes, which can oscillate back and forth inside the cavity without decaying. Now you see, all these discrete frequencies seen here are actually cavity modes. We have already discussed about these modes. These are the cavity modes, and the spacing between the cavity modes is free spectral range, which is inversely proportional to the cavity length. So all these discrete frequencies you see here are cavity modes. Of course, there are many more frequencies, all are. I have not only shown them here. Numerous frequencies are there which are resonant to this cavity. Now see, all these modes, all these frequencies which are cavity modes, which can oscillate back and forth inside the cavity without decaying, and all these cavity modes have gain, small or big. All of them have gain. So does it mean that lasing would occur on all these cavity modes? The answer again is a big no. To understand this, let us go a bit deeper. You see, for a typical laser, one of the cavity mirrors, so this one, is maintained generally 100% reflectivity. That means no light can leak through this mirror because its reflectivity is 100%. Whatever light shines onto it, everything is reflected back. So no leakage of light is possible through this mirror. What about the other mirror? That is the partially transmitting mirror, which actually allows a part of the light to be leaked through, and this is a useful loss which forms the output beam of the laser. So this is the partially transmitting mirror, and of course it is not shown here, but you must know that one of the mirrors, so this mirror, is slightly concave to make the cavity stable. If both the mirror are plane, then it will be very difficult to stabilize the cavity, as we have seen that even slight deviation from parallelism will simply make the light walk out of this zone. So then, where were we? Now, lasing can occur only on those frequencies already. So we have provided some transmission loss on this mirror. Now this transmission loss is independent of the frequency, because the reflectivity of the mirror or transmittivity of the mirror doesn't depend on the frequency. It is independent of frequency. Therefore, this loss can be represented as a straight line in this gain curve as a loss line. This is parallel to the frequency axis because it doesn't depend on frequency. So all these modes, cavity modes, will experience the same loss, which is given by this is the gain. Different modes have different gain, but all the modes have same loss, which is represented by this straight line. So now, lasing would occur only on those cavity modes which have net gain, meaning whose gain is more than the loss. If a mode exhibits more loss, then round trip loss, as the light, that mode frequency travels to and fro. So start from here, travel to this mirror, and come back here. As it travels and comes back, it actually experiences gain because it travels through the population inverted medium. So as a result of stimulated emission, the number of photon increases, therefore the intensity builds up. Now as it comes here, it exhibits the loss, experiences the loss because of this mirror. Part of it is leaked out. We have seen earlier that if the loss, round trip loss, exceeds the gain, the oscillation cannot sustain. The same logic also applies here. You see, the modes for which the gain exceeds loss only will be able to oscillate, will survive. Rest of the mode will not be able to oscillate. Now you see, in this particular example, you see 1, 2, 3, 4, these five modes have gain exceeding loss. Therefore, they only will be able to laze. The other modes, although they have some gain, but the loss is much more than the gain. Therefore, they would not survive. And hence, the lasing would occur only on these 5 modes. And the emission feature of the laser would look somewhat like this. The mode, in this case, this mode which is indicated by 3 has the highest gain, and therefore this also gives rise to, provides higher output. Say we the intensity of power of the laser as a function of frequency. So the mode with higher gain also will yield higher power, understandable. Now, you see another interesting point is that, therefore, essentially, this laser is a multi-mode laser because this laser, there is oscillation on 1, 2, 3, 4, 5 modes. Although the monochromaticity of this laser, this multi-mode laser, is more than that of a conventional light source. For example, suppose if we consider this medium as a medium which emits light. Suppose we do not have this cavity, and you have not created population inversion. You have just created some excitation as in the case of a fluorescent source of light. So this excited atom or molecule, whatever, as they come down to the ground state, they will emit spontaneously light. What will be the broadening of that light? The broadening will be just this. This is the spontaneous broadening. Therefore, a conventional source of light using the same medium will give you a spectrum, the broadening of which will be this. But this, when you make it a laser with using this medium, putting it inside a cavity, creating population inversion, the emission width of the laser lies because these 5 modes will only be lasing. Therefore, the monochromaticity, which is determined the emission rate, is better than that of a conventional source. Conventional source width is much too bigger, much too larger. True, this multimode laser has a monochromaticity better than that of a conventional source, but surely it is not a highly monochromatic source because so many modes are actually oscillating here. The monochromaticity of the laser can be significantly improved by restricting the number of oscillating modes. This can be achieved in a number of ways. First, the broadening of the gain can be reduced, so much so that now only a fewer number of modes actually experiences a net gain. For example, you see let us assume somehow we have reduced the broadening of the gain. So how you can reduce? You increase the lifetime of this level. If you increase the lifetime, then the broadening will reduce. Heisenberg's uncertainty principle. How we have reduced the lifetime will come in a while. So if you reduce the broadening of the gain, then you see, in this case, as you can see, it has been such that only one mode, this mode alone, has gain exceeding loss. No other mode, even so this mode, it has some gain, but the loss is much too big for this mode. So, lasing now would occur only on this mode, which has net gain. So the emission feature in this case would be like this, single mode lasing. In this case, the laser is lasing on single mode. So then the emission will be highly monochromatic compared to a multimode laser. See, again you see, it is the cavity which is doing all the tricks. The same also can be achieved simply by reducing the cavity length. We have seen that if you reduce the cavity length, then the free spectral range, that is the spacing between two adjacent cavity mode, increases, because free spectral range is inversely proportional to the cavity length. Shorter the length of the cavity, the more widely the modes will be spaced. So I have shown it here. So if this is the case and our gain is just as it was before, and now instead of reducing this broadening of the gain, we have increased the spacing between the modes by reducing the length of the cavity. So then what happens? You have once again created a condition wherein only one mode, I mean this mode, has a net gain. No other. These modes are so far away that though they hardly see any gain. While the loss is when you are independent of frequency loss, there is so much of loss and there is hardly any gain. So once again, lasing will be affected here only on this mode. So this will once again be a single mode laser. We have attained single mode operation of this laser in two ways. One is we have reduced the broadening of the gain to ensure that only one mode has net gain, and therefore lasing is restricted only on that. It is a single mode laser. That means the emission is highly monochromatic, or we have reduced the cavity length so much so modes are so widely spaced that once again only one cavity mode has net gain, and therefore lasing is once again restricted on single mode. But in both these techniques, the monochromaticity has been attained at the expense of the operating performance of the laser. I will explain to you how. Now you see, how do you, for example, let us consider the case of reducing the broadening of the gain. How do you achieve it? Let us consider the example of a gas clip, where the active medium is a gaseous medium, which has given that particular broadening of the gain because of the lifetime, so lifetime that is associated with the blazing level. And the Heisenberg uncertainty principle is the determining factor. Now, if you have to reduce the broadening of the gain, how do you do it in a gas laser? You, of course, have to reduce the operating pressure of the laser. If you reduce the pressure of the laser, that reduces the collision frequency. Less molecule or atom means they will collide less frequently. So collision frequency. And if the collision frequency is less, then once you have excited an atom, a molecule, higher energy state, then if this excited molecule collides with another molecule which is in the ground state, then this collision will actually relax the molecule from that excited state. That means more collision means shorter lifetime. And less collision means the molecule can spend longer time in the excited state. I think it is clear to you. So if we increase the pressure, there will be more collision. That means lifetime will be reduced. So the broadening, if the lifetime reduces, then the broadening increases. Heisenberg's uncertainty principle. So if you have to reduce the broadening, you have to reduce the pressure. Because if you reduce the pressure, the collision frequency will be less, so the excited molecule can reside in the excited state for a longer time. So if you have to reduce the broadening, the gas pressure, you have to reduce the operating pressure. Now, operating pressure means you are reducing the density of the active molecule, which actually provides you the output, lasing output. If there are less excited atom, that means you will generate less number of photons. So the power of the laser will be less. So if you reduce the pressure to get monochromaticity, this has been attained at the expense of the operating performance of the laser. The laser is giving you less output power. I think it is clear to you. So in the first case, the monochromaticity has been attained at a reduced output of the laser. In the second case, you have actually reduced the cavity length. Now, reducing cavity length means you are bringing the mirrors closer. So how can you do that? You have to reduce the active length. So to bring it closer, you will have to reduce the active length. If you have reduced the active length, that means what? Once again, you have reduced the total number of active atoms that can give you laser output. So once again, this reduction in length that gives you monochromatic output has been attained at the expense of the operating performance of the laser. Laser is giving less output. The same, however, can be achieved at no expense of the operating performance of the laser by going for a dispersive cavity, as I show here. What is a dispersive cavity? You know that if you have dispersion, if you have a prism, and if you shine this prism, the white light, then the light, after it passes through the prism actually splits. The white light consists of many colors. prism actually splits this light spatially into their different wavelength components. This is the big gear, you know. You actually exploit this property, dispersive property of a prism. There could be other dispersive element also. Let us consider the case of a prism. That is very simple to understand. So you have placed a prism inside the cavity, intracavity. That means between these two mirrors. Now you see this mirror is now slightly oblique. That is because the prism has split, dispersed the light. So the other mirror is in a awkward position. But you are exploiting this property to get once again single mode operation. You see, in the beginning, this active medium, actually it is the oscillation begins from spontaneous emission. The spontaneous emission, you have all the wavelengths present, and out of these wavelengths, those modes initially that you're say there are 5 modes that I say that we saw would lay in that laser if there were no prism. Now these modes, when they shine on the prism, what prism will do? Prism will split them into their constituent colors. Different modes have different wavelengths. So different wavelengths will travel to the prism in different direction. Let us assume that these are the 3 modes. So the 3 modes, prism will split in 3 different angles. Now only one of them at a time will fall normally on the output mirror, as you can see here. So this mode alone will then be able to get feedback. See, it will be oscillate back and forth because this has fallen normally, so it will also reflect back in the same direction, and then it will travel to the other mirror, and there also it will fall normally, and then will be again reflected back. So this mirror alone would be able to oscillate back and forth. Other modes which fall obliquely on this mirror would be reflected away and just would get lost, would not get a chance to laze at all. And this mode alone would be able to oscillate back and forth and extract energy from this medium, active medium, which is continuously being pumped to maintain population inversion. Other modes cannot extract any energy from this active medium because they have no chance. This prism has come on the way. So this laser again will give you a single mode laser, but now at no expense of the operating efficiency of the laser. Another advantage is that you can tune the laser. That means you can choose different modes, different operating different wavelength of the laser or frequency of the laser by tuning this mirror. Suppose you tune this mirror in this direction, like this. If you tune it like this, then this mode will fall normally on this. So it will be reflected back, and this mode now will be reflected away, and so will be this. So by tuning this output mirror, you are actually choosing different wavelengths. That means you are able to tune your laser, monochromatic laser, and the monochromatic output you are able to tune. So cavity actually has allowed all these. And this tuning can also be done by tuning the prism instead of the output mirror. So then, you see, the cavity has given laser lot of almost all its attributes. First of all, directionality, which comes from the property of stimulated emission, and cavity allows to exploit it. Then cavity allows the laser to become more and more monochromatic. It allows is the tuning of the output of the laser. I think I'll stop here and we'll begin our next class right from here.